Okay, here we're going to look at a different method for doing volumes of revolutions called the method of cylindrical shells. So now we're going to build up a bunch of cylinders, cylindrical shells, like labels of soup cans, going outward to fill in a volume. That's the idea. So say we've got some function here, and say we've got some region bounded below that function, and, between that and the x-axis. And maybe we rotate that around the y-axis. So we get some volume that looks like this. Now, like you can read through all this where we very carefully show like all of this here, show what the volume of one of these shells are going to be and so forth. There's a better way to think of this. I'm not going to go through all these boring details here because I don't think it's instructive, but read through it anyways. Here's the idea. I'm going to pick some little slice here and build like a little rectangle, and I'm going to rotate that rectangle around to create this hollow cylinder here. So I've got some outer radius here and some inner radius. Kind of looks like a washer. You might be thinking, Professor Pertee, this is just washers. Yes, it really is a washer, but it's really tall. Like, I don't think you would ever be putting together IKEA furniture and have a washer that's that tall and this thin. The walls here of this washer are some little delta X. And we're going to let that delta X go to zero so that this becomes like paper thin. It becomes infinitely thin, and we build up our shape by adding on soup can labels from the inside all the way out. Imagine you just keep adding on hollow shells like this to the outside of what you already had until you build up the entire volume. So we've rotated here around the y-axis, but my little differential here is going to be a dx, a little delta x. With cylindrical shells, whoever you rotate it around, you integrate with respect to the other guy. This is different from what we did with washers and discs. So imagine we've got a whole bunch of these shells, all like Russian nesting dolls stacked inside of each other. What's the volume of one of these shells? Well, the best way to think of it, again, they go through a nice derivation here to get this. But a better way to think of it is take one of these shells and cut it and roll it out into a rectangle. Okay, well, this distance there, we could call that the height. In this case, that's just the function value right there. And what's the length here? Well, that's just the circumference going all the way around. And circumference, of course, is 2 pi r. What's r? That's my x value where I built this thing. Okay, what's the volume? How thick is this thing? What's that distance there? Delta x. So the volume of just this little shell, this one shell, length times width times height. It'd be 2 pi x, because that was this distance, x. That's the radius. Times the height, f of x, times my thickness, delta x. And then, yeah, again, we use a Riemann sum. I think we built a Riemann sum in here somewhere. I guess they don't explicitly write it out. So we would add up all these shells, take a sum, I equals 1 to n, take the limit as n goes to infinity, which is the same thing as taking the limit as delta x goes to 0. Oh, there it is. I knew there was a Riemann sum in here somewhere. When we take this limit, this Greek letter S becomes our letter S elongated. That delta X becomes a dx. So if we want a formula for the method of cylindrical shells, here's our formula. This is not the way I want you to think of it, though. That right there is the radius, and f of x is the height of that shell. That's the way I want you to think of it. So you've got some shell here. Let's draw this maybe in blue. This distance here is the radius r, and this guy here is the height h. Okay, let's take a look at an example. So we've got this region bounded underneath 1 over x and above the x-axis from 1 to 3 that we're now rotating around the y-axis. Now, could we just use disks? Probably. The problem is, if I were to try to stack up washers here, like say I took like this little rectangle here and I rotated it around, I get another piece over here. Well, my outer radius is going to change. Look, for in this entire region in here, my outer radius is always 3. Oh, until I get to here, now my inner radius, my outer radius is now 1 over x. That function. In terms of y, that would be 1 over y. When I switch from this to this, my outer radius changed. So like, let me draw this in red. I want to make sure you understand why we're even learning a new method. At this spot, if I were going to use washers and stack them up, that would be an outer radius right there. But here, I have a different outer radius. The inner radius is always 1, but the outer is going to change once I get to that spot right there and I'm stacking these guys up. We could probably do it, but it'd be a pain. So what we're going to do instead is take a slice this way, have some delta x. So this rectangle, always draw your rectangle, is going to get rotated around. So he'll have a buddy over here that he hits on the other side. And like I could try to draw in this one shell. Okay, so remember the volume of a shell for any shell is 2 pi r h. R is the radius from the axis of rotation to your rectangle. H is the height of your rectangle. Notice here that we are integrating with respect to x. I've got a delta x. Everybody needs to be x's. All right, so my radius here is always the same. Okay. Yeah, I almost confused myself for a second there. My radius is always x because I'm out at some location x. Remember, we're going to be building all of these all the way from here all the way out to here. So that radius is changing, and that's at location x. So I know that. The height, that's this distance here. That's 1 over x at location x. Okay, when is this true? From here, this would be the smallest x. So here's my start. The smallest x where that is true, all the way out to here, end, from 1 to 3. So we get the definite integral from 1 to 3, 2 pi r h dx. And then like you can do this integral on your own, check and make sure you get that. Okay, now we're going to rotate around the y-axis. That one we rotated around the y-axis. We're going to do another one. So I've got this region. Like read the words and make sure you understand how they came up with this region. Bounded above by this graph and below by the x-axis. Over the interval from 0 to 2, rotated around the y-axis. Could we use washers? Maybe. So let's draw in. We're rotating around this way, so if I were going to use washers, they need to stack up. They need to look like this. So I would draw in some little rectangle here. I would have his buddy over here. And this is all rotated around. I'm just kind of quickly showing you why this isn't going to work. Because if I tried this, my outer radius here would be the distance from the y-axis out to this side of the curve. And then the inner radius would be the y-axis to this side of the curve. And I would need both of those to be functions of y because I have some delta y as my thickness. I would need to somehow write this side of the curve as a function of x or function of y, and this side of the curve as a different function of y. So you would have to kind of try to find the inverse of this, but it's not invertible. So you would have to, okay, well, for x greater than 1, we would have this curve and write that as x equals some function of y for both this red side and this green side. Is it possible? Probably, but it'd be a lot of work. The reason we have these different methods is sometimes it's easier to do the integral using one method or another, and sometimes it's easier to write the integral using one or the other. If we use cylindrical shells, then we pick some x value here. Sorry. Draw in my little rectangle. I don't know why it's not switching to blue. Sorry. Draw in my little rectangle that's going to get rotated around to build my shell. Has some thickness delta x. Oh, I'm integrating with respect to x. That gets rotated over to here somewhere. On the other side, I can try to draw what that shell will look like. Okay, so my thickness I know is delta x. All right, what about my radius, r? Oh, that's just this x value that I picked randomly. What about my height? Oh, my height is just the function value. H is the function value. R is x. And thickness is delta x. And for which x values will that be true? From 0 up to 2. For all of these x values, the height is always that function. So 0 to 2, 2 pi r, that's the radius of my shell, and that's the height of the shell. And that's the thickness of the shell, the dx. And then again, you can check all those details. Okay, let's look at another one. What if we're rotating around the x-axis? So here's the formula we'll use. Y there, when they say Y, they mean the new radius. And when we say G of Y, we mean the height. And by height, we're going to mean something that's turned on its side. You'll see. Okay, so we get this region bounded by 2 square root of Y. And then on the left, bounded by the y-axis between y equals 0 and 4. And we're taking that and rotating it around the x-axis. Now, we could try doing washers. So I could take something like this and rotate it around, get another washer that, or the other side of the washer, the other half. So this got rotated like this. So this space is empty. And then I'm so bad at drawing these. I hope you can see that. My inner radius would be right here. My outer radius would be right here. Yeah, it would work. We could absolutely do it. I would have some thickness of delta x. I would need this guy in terms of x. So I would need y equals a function of x. And then my outer radius would just always be 4 the whole time. That would work perfectly fine. And maybe for fun, we'll do that. But that's not what the question asked us to do. It asked us to use cylindrical shells. So with cylindrical shells, if you're rotating along around the y-axis, I need my rectangle to rotate around the y-axis. So I pick some rectangle here at some height y that has some thickness delta y. And that's going to rotate over. I know the picture's right beside me, but I'm trying to draw a separate picture here. So that guy got rotated out towards your eyeballs, hit there, and then it goes back behind the screen and so forth. Okay. So the radius of that shell, here, maybe I'll try to draw in this shell. That was terrible. The radius there is just that y value that we picked. And the height, always, the whole time, is just this function. That distance right there. The thickness is delta y. That's always true all the way from y equals 0 to y equals 4. So that right there was my radius. And that right there was the height of that cylindrical shell. Okay, now let's do one where we rotate around a line that's not one of our axes. So I've got y equals x. From 1 to 2, and above the x-axis, this little region here, rotating around the line y, or x equals -1. Again, we could probably do it with discs. We could use washers. So I could take some little rectangle here, rotate that over here. So it would be 2 units back. It would be like right here where it gets rotated. Because remember, we're rotating around here. The problem is, once I get up here, in this case, my outer radius would always be 3. 1, 2, 3. That's the outer radius. The inner radius would always be 2. But once I get past this level, now the inner radius changes and is a function of height. So we could write it as 2 separate integrals. There are ways we could do it, but it's a lot more work than just using cylindrical shells instead. So take some little sliver here that has some delta X thickness. So we rotate it around something parallel with Y. We're integrating with respect to X. This guy's getting rotated around. I'm at some location X. My radius is not X. It's this whole distance. This is X. That radius is X plus 1. If you're not rotating around one of the axes, you got to draw a picture and you got to look at it. My height is y equals x, the function. And remember, volume of a shell is 2 pi r h times delta x, your thickness. There's r, there's h. We're integrating with respect to x. Now, what are my starting and endings? 1 to 2. So that's what I'm calling the radius of my typical shell. That's the height. And again, you can check all the details. Okay, that's a good place to stop on this one.